Welcome to the Gregarious Mammal Podcast. This is Chris, and in this episode, I have a moderately long but interesting interview with the infamous Stephen Wolfram. I did this interview at the Collision Conference in New Orleans. There was quite a bit of background noise. I've tried to clean up as much as possible, but persevere. It's an interesting interview with one of the fascinating stalwarts of the computing industry. So please enjoy.
A lot of people have heard of one particular Wolfram product, so maybe let's kick off with who you are and what Wolfram is as a collective.
Yeah. So, I started the company 32 years ago, and we've kind of had a single vision all that time, which is pretty cool in the tech industry because most people don't get to be building a technology stack consistently for 32 years, so to speak. And the kind of the core of what we've done is this thing we now call Wolfram language, and it kind of the most visible pieces of that were Mathematica, which came out in 1988, and Wolfram Alpha, which came out in 2009. So,
is it that recent? Oh wow, I think it was older than that.
Well, I see that thing that has been quite old by now, but yeah,
I suppose.
Right. I mean, so kind of the and our products. I mean, Mathematica is primarily used in the R&D sector and in education. So most major universities have site licenses for it and things. It's been used for all kinds of interesting inventions and discoveries over the years. Then Wolfram Alpha is used by, a decent fraction of the students of the world, as well as lots of professionals and so on. And it's a kind of a drive-by computation system where you're just typing in natural language and, you get answers. There's actually a branch of the Wolfram Alpha business, which is the enterprise Wolfram Alpha business, which is something that has been growing rapidly, although it's probably we're going to end up spinning it off in some way because it's really not that central to what a lot of what we're doing, but it has to do with building versions of Wolfram Alpha customized to large companies dealing with answering questions about their internal data as well as questions about the world in general. The Wolfram language, the big idea there is something crazy that nobody else has done, which is, build a language where you build in as much as possible about knowledge, about computation, and about the world and data and so on as you can. And that's, my goal is to sort of make it as automatic as possible for if you can conceptualize something computationally, then my job as a language designer is to get it so that you can take those thoughts and as automatically as possible actually create, a program that makes use of that. And I think I view it as being kind of this layer of computational intelligence that we're trying to make increasingly ubiquitous in the world. And actually, I think there'll be some things in the next probably 6 months or a year where we're helping to sort of add to that ubiquity. I mean, the thing that's happened, our stuff has been widely used, as I've mentioned, in R&D and in education. It has, until recently, not been widely deployable in enterprise settings and in production settings. We've changed that over the last, 8 years or so. We've been working on building out cloud infrastructure, embedded infrastructure, and so on, and that's now really quite well developed. And it's, our stuff is getting used in a bunch of production settings at large companies and so on. And that, what does it look like? You're writing Wolfram language code, which is very high-level code. It's fun for me that I can see that, the world's fanciest R&D folk are writing the same code as, middle school students can write, so to speak. I think that's kind of fun. It's also fun when developers say, oh my gosh, it's so hard to learn all this stuff. And I know all these 12-year-olds who know how to write this code.
It's too simple for it.
Yeah, right. Well, yeah, I think there's a certain sense in which people say, it's not code unless... what's happened in the world of programming languages is that there's an awful lot of, there's some nice designs and so on, but, fundamentally the concept of programming languages has changed rather little in a very long time. It's basically been...
Object-oriented was probably one of the last big kind of...
Yeah, but I mean, yeah, right. But I mean, I think the point has been that, what is a programming language? What is the point of a programming language? I mean, people see it as being, okay, you're going to, the computer has certain operations that it does. We're going to specify what sequence of those operations it does, and then we're going to provide a lot of kind of superstructure support of, how to organize a large program, those kinds of things. And that's what a lot of the distinctions between programming languages have to do with that. My goal has been something very different, which is don't build the small programming language that's sort of wrapped around the specific operations a computer can intrinsically do, but rather build a large programming language where we go to a lot of effort to maintain design consistency over a long period of time. And I'm kind of proud of the fact that, you can take a Mathematica version 1 program and
I'd actually like to dig into that, because you mentioned that in your talk yesterday. You claim, I don't know if you claim 100%, but you claim backward compatibility to version...
Pretty much.
0, version 1.
Not before version 1. I wouldn't claim before version 1.
Which is pretty amazing. Most products struggle to the last version. Back to so, and then I guess with all the constant changes and trends in developing applications, how have you managed to do that? And how many times have you rewritten everything? Or has it always just been...
What we've been... Okay, so there's different things. So there's the code base... I don't know, Wolfram language is probably now 50 million lines of mostly Wolfram language code, and then Wolfram Alpha is another 15 million lines, and then there's God knows how many tens of terabytes of data and so on that go with all of this. We've been very consistently able to just build. Our major components, I mean, I'm actually upset that there's code of mine that's still in the system from back in 1987 and so on. Some which I'm told works just fine, so nobody wants to replace it. But generally, our algorithmic code, we, when we attack an area, we do it in a very, complete way. And, the replacement time is probably 20 to 25 years for the sort of algorithmic. When it's, there's development in algorithms that lets us do things more, but in terms of the actual code base, it's surprisingly, well, not surprisingly. I mean, we just, we make an effort to get it right, and that's so. The whole picture is a little bit more complicated because we tend to, there's stuff that's a part of the core chassis of the system, and there's stuff that's kind of on the leading edge. And sometimes, I've learnt over the years in terms of design, how to do sort of defensive design for the leading edge. So, and, some of our stuff we tag as experimental, and then we don't consider ourselves, constrained to maintain that, although that's a small fraction of the functionality these days. How did I manage to get this more or less right and not regret too many things that were in version 1? That's a good question, right? So the first answer to that is because I had built a system before in which I made many of the mistakes that I might have made in version 1.
Fair enough.
And I built a system called SMP that first came out in 1981, and I started a company based on that, which eventually went off in different directions. But in SMP, what I had done... So, I started life as a physicist, and so I kind of my approach to language design is kind of, a little bit like natural science. That is, you think about sort of all of the computational operations people want to do, and then you say, what are the fundamental building blocks? What are the primitives from which all this stuff can be built? And it's kind of like, go find those primitives, like go find the atoms and quarks or whatever, that from which you can build up computation that people want. And so, what I did back in the late 1970s was I really dug into, what is the fundamental way we should think about computation, and this kind of approach of symbolic programming and representing everything symbolically was pretty much, it's the approach that's been used for the last 100 years or so. It's not an approach that's gotten into most of the modern programming languages, and it's also an approach where, in SMP, it's a more extreme version of symbolic programming than Wolfram language, so I got to make many of the most obvious mistakes in SMP, and by the time I was doing, Wolfram language in 1986 to 88, the first iteration of things I don't think I got wrong. And I think, what's happened now it's one I've been doing language design for 40 years, so it's kind of there are lots of kinds of things where I think I've gotten pretty good at knowing when I know what I'm talking about, so to speak.
Has it always been written in the same languages, or
so in Wolfram language?
Yeah.
I mean, so originally it was written in an extension of C. The kernel, it was before C++ was really useful, so we built our own object-oriented extension of C back in 1986. Then mostly it's still the absolutely raw internal kernel code is still C, mostly C. A very large fraction of the code base now is written in the language itself.
Yeah.
In fact, we've had various compilers for the language. We have been for the last 5 years or so working on a very ambitious, really full compiler for the language, which is very cool, actually. I mean, it really compiles down into LLVM code, and it's it's rather spectacular, actually, because it will go from this very high-level symbolic code into something that's completely, that's executable standalone and all kinds of cool things like that. What happens, the thing to understand, I mean, for me, building a big language like this, maintaining design consistency is kind of a key element, because, you have 5,000, 6,000 functions. Unless there's real consistency in how that works, the whole thing kind of flies apart. And when you do have consistency, spectacular things happen, because you get to, you think you're building out one component, but actually you can make use of all these other components.
Sure. Yeah.
And one of the things that's been notable to us is, in terms of algorithm development, for example, you think you're making a, numerical integration algorithm. But actually, in doing that algorithm, you need to use graph theory and computational geometry and algebraic analysis and so on. And because for us, those things are sort of free because they're already in the language, we get to build these much fancier algorithms than we would otherwise be able to build. And that's been, so, which means we can end up with much more efficient kinds of processing than one could do if one's like building things from scratch and so on.
And what's the crossover between the various products that Wolfram has and things like Jupyter notebooks?
Well, Jupyter notebooks, I think they will say, are kind of a rip-off of our notebook technology. They're pretty lame compared to what we have.
Yeah.
I don't really know why. I think people... It's an interesting thing for us. I'm a great believer. I'm a very simple-minded business person, and I kind of believe in, trying to make a business where the value people get from our stuff is what pays for us to develop more stuff. And, I've been lucky enough to have a, consistent business for 32 years. It's not, it's a modest, it's 800 employees, so it's not a huge...
That's actually, I consider that fairly large. So.
And it's almost all R&D, so it's very little commercial operation, which is something that is unusual, and, we probably would be a 50 times larger company if we had focused more on... more on kind of the, let's optimize the commercial side of the business. It's something where a lot of stuff we've done, like Wolfram Alpha, we've kind of given away to the world. It's kind of cool that all these people use it, and I'm not sure. We don't run ads on it. We don't monetize it at all. Actually, the main website, Wolfram Alpha is monetized through the enterprise version and through the APIs that we sell and things like this. With Wolfram Language, we have a kind of an open cloud where we're making that available for free, and actually we're increasingly going to be making available, something developer crowd will be interested to hear. The kind of our goal is to make the language sort of free for development. It's hard to figure out exactly how you slice that, because, if somebody's going to run, the truth is people don't really want to run a giant production system off a free, nobody's supporting this kind of thing.
It's a thing that a lot of developer tools have looked at. I've worked for a few developer tool companies myself, and this point of where do you switch the self-serve developers to an actual product and encourage them or someone above them or around them to pay for something
Right.
To the challenge.
Well, I mean, we're in the position where the R&D world pays for our stuff, and for people within the R&D world, like at universities, most major universities have site licenses for our stuff, so our stuff is basically free to people within those universities. And, like it's bundled on the Raspberry Pi computer, so it's free to people using Raspberry Pi. I think my goal is to have a business where basically we, where the people who are getting value for what we do pay for us to go on developing stuff. And I think it's interesting because I've been very curious. I follow a lot of open source projects. We use a lot of open source stuff. We contribute to a lot of open source projects. We're big contributors like to MXNet, which is a big neural network thing. I think we're the number 3 contributor last I looked to that. It's like, how should we think about modern software licensing? And it's,
My last interview was with the lead of the JS Foundation. We were talking about this. Yeah.
Right. I mean, I think that the situation we're in is that, we've had a modest but successful business for a long time. And, from my point of view, the thing that we have is kind of this layer of computational intelligence, which should be ubiquitous. And, because we want to make it so that, when you write code, if you want to know, what was the average temperature in New Orleans in April or something, that's just something that you can assume that you can have your program know. Or if you want to be able to do natural language understanding on some place name or something like this, or natural language understanding of some date or something, that all of that stuff is just part of the language, which is what we have. Yeah. But, the thing that I see as being the really interesting thing that I want to have as sort of, part of the legacy of our efforts, so to speak, is, if we look at the history of computing, it's kind of been, okay, there are the simple languages, there's operating systems, there's UIs and so on. This layer of computational intelligence, that's what we've just spent basically, I've spent about 40 years building. And, I want to make that as accessible and ubiquitous and as effectively used by people as possible. And I think that's, what you can do with it is quite magic compared to what you can do with, a lot of other things that exist. Yeah. And, the challenge, I would love to have the question of exactly how you arrange licensing so that the right things happen is an interesting question, which I think we've actually got some pretty good solutions to now.
Yeah, and actually I'd like to, let's go down that path. So you're someone who's been in the software development industry for a while, and you've obviously seen opinions come and go on things like licensing. So artificial intelligence is not a new technology, but it's come of its age right now.
Yeah.
And then even, I read your blog post a couple of weeks ago with the huge title. I can't remember the exact title now, but it was buzzword full.
Yeah. Right.
And you've been writing a lot around blockchain as well, which again, conceptually is not new, but the technology has come at a time where it's relevant. I was sent a draft of one of your next posts as well.
Okay. Which I still have to work on. If I didn't have this cold, I would have been working on it. But
it seems that the most interesting aspect of the blockchain space, especially to you, is the contract side.
Well, yeah, because we have a language that can represent the real world,
exactly,
which is what you need if you're going to write a computational contract. But coming back to this, I think you were kind of one's seen a lot of trends, in terms of software licensing, for example, one of the problems is that enterprise software companies have a terrible habit of just outrageously gouging their customers. And, I know this from, as a consumer of these things. We have been, for the last 30 years, it's probably a terrible mistake, but we've been tremendously consistent with our pricing and so on. And it's been, it's like, I'm not sure anybody notices, except our customers are, don't get unhappy, so to speak. But it's, my point of view is, and, there's a lot of this, the thing is free, but we're going to, sell all your data. or the thing is free, but oh well, if it breaks, tough luck, or the thing is free, but you have to spend a lot of your effort to set it up. My point of view is, my ultimate goal is to get the stuff we've built be used as broadly as it should be used, while also doing something where I can, go on consistently building this stuff, for as long as I'm able. And I think also, the thing to understand about what we do is, because there's all this knowledge and so on built in, we also have all kinds of other licensing tentacles with other people, because we're licensing their data and et cetera, et cetera, et cetera. And it's a whole fairly complicated ecosystem.
Yeah, but you showed maps and you showed all sorts of examples yesterday.
Yeah, right. Well, they're right. So I think, my belief is, we made a bunch of stuff free to people who are kind of sort of tourist users, so to speak, and people who are, trying to build things. Once people are really going into production, they actually don't want stuff to be free. They want somebody consistently maintaining...
Someone to be able to shout at when there's a problem.
Right. And I think that's, and it's actually interesting, I've certainly taken as an exercise for myself, turning SLAs into computational contracts and figuring out, one of my little goals, which I haven't succeeded in so far, is can we make the license agreement for our developer use of our stuff actually into a computational contract that is self-executing.
And then this comes back to the smart contract world, which is still... I interviewed yesterday the Hyperledger people, and I've spoken to them before, actually, and they have this concept of trying to make a smart contract describable by a business person. And they're halfway there, but it's still describable by a business person.
Look, the language that in Wolfram language, one of the things we've achieved is this language which can talk about things in the real world. Yeah. So, and it also happens to be able to interface with IoT devices. It happens to do machine learning. Yeah. And so when you think about, what will a computational contract look like? Well, it'll involve things about the real world. It'll involve, measuring things from IoT devices. It'll involve a bunch of things like that. And we have a great language for doing these things. How does it relate to blockchain? Well, there'll be many computational contracts that have nothing to do with blockchain.
Sure.
But what's interesting, I think, about computational contracts is they're a form of computation where it's just an autonomous thing. You just say, here's this thing that I want to have happen in the world, lodge it somewhere in the computational infrastructure, and have it come to life and do its thing when it thinks it's relevant, so to speak. Yeah. And that's a slightly different form of computation. And so for me, thinking about, our technology stack where we're, desktops and, cloud and embedded devices and mobile and so on, autonomous computation is another use case, which is sort of interesting to think about. And, I think we have sort of a unique thing to contribute there.
Yeah, actually, I think you're right. It's certainly a sort of missing component in that world at the moment of, an aspect that people can describe and be able to use a natural language is certainly worthwhile. Actually, on that note, is as much as any programming language has always tried to be more human readable, they often tend to be human readable English. Is the Wolfram language purely like English lexicon, or is it also...
you can get, in about 25 languages, I think, these days, you can get what we call code captions, which is if you... in the cloud and on desktop, if you switch on code captions, it will give a phrase that translates every function name in a native language. And in fact, we've sort of interesting. That has not been as successful as I thought it might be. And the reason is...
used to use any English sort of...
Well, the place where it's important for us is when it's for K through 12 kids in different countries. It's useful. I think the thing is that people, because English is really the only language I seriously speak, it's not... I don't have a great intuition for the sort of switching time that people have between. I think it's useful for people. Actually, for me, it's kind of amusing because I can learn a little bit of other languages by turning on code captions and seeing other things. But the idea of so that's in terms of our Wolfram language. In terms of our natural language input, yes, actually, we have a version of Wolfram Alpha actually in Chinese, which is still not deployed for various stupid Chinese government issue reasons.
There's a lot of them.
We have versions actually in 5 languages, which will be coming out soon. So a lot of our natural language understanding stuff will work in at least 5 other languages. I think the use of natural language understanding within the Wolfram language, not by users of the language, but by developers in the language, is something I had not really anticipated, but it's super useful. I mean, like if you want, the city of New Orleans or something, you just type Control equals city of New Orleans, and that natural language will get translated into a precise symbolic representation. There'll be a little ... that is the disambiguation thing that you can press. If it didn't give you the right thing you thought it should be giving you, you press the ... and it'll show you all the other possible disambiguations for that concept. But this idea of taking fragments of natural language and, starting with those and then turning them into precise symbolic language, that turns out to be a really powerful thing. That is it's a very good way. I hadn't really internalized this properly until we built it. That's a really good way to leverage natural language. I mean, you can write. Okay, so you might say, can you write code in natural language? Right? And I think the answer is not in a very sensible way. So, I had a sort of good case in point of that because I wrote this book for kids and others about Wolfram language, and it has exercises. And the exercises typically say, they typically are a piece of English that says, write a piece of code to do blah. Yeah. Right? At the beginning of the book, very easy to write the exercises. By the end of the book, it's like these exercises are really frustrating to write because I know immediately what the Wolfram language code is that I'm trying to ask people to write. Sure. But translating that back into English is actually quite hard. So, I think that was kind of heartwarming for me as a language designer to see, because it's like, yes, there is actually value to making a precise symbolic language that can represent these things. It's not just, natural language is not sufficient. And I think, programming, little sort of drive-by programming of the kind that people do in Wolfram Alpha, that works well in natural language. Building bigger structures, you can get little pieces in natural language, but the full thing is really a structured language is what you need. And I think, this whole process of designing a language, so one of my goals is to make it a language that helps people think about things computationally. And I've noticed that when people know Wolfram language well, one thing that's always fun for is, when you're fluent in Wolfram language, it's very obvious people are starting to type before they could verbally express what it is they're actually going to. Possible. Right. But I mean, they're just, one is fluently thinking in the language, and what ends up happening is there are lots of ways of thinking about things which are very clean and efficient, and which one learns from structuring things in the symbolic language. So there are things where, I could say, I think about, in fact, for a lot of, when we're designing stuff, it's always, there's this big piece of functionality. Okay, what's actually going to be the function that represents this, and how does that relate to the, the existing structures that we have? And then sort of, there's it's hard to describe this, I suppose, but it's kind of, the goal is to have a language in which, it actually helps you to think about kind of the computational process to have that language as a medium to think in.
Yeah, and the inputs into the next step and things like that. That was sort of something you were demoing very much on the fly yesterday.
Yes,
piping,
right.
There's the concept of pipes in many languages, but thinking of it in a more natural language way helps you understand how those things relate.
Yeah, I mean, for us, it's a functional language. So one thing about symbolic languages is, of which there are almost none in the real world, so to speak, except for ours. One feature of our symbolic language is any code fragment is meaningful. So you don't have to have a harness of other stuff because it takes symbolic input, it generates symbolic output. So at any stage, there's always a meaningful construct that you can produce. And it's somehow, the other thing that's important about symbolic stuff is that anything can be represented. And this is the thing that, again, when I started designing Wolfram language a long time ago, I thought sort of symbolic expressions were a good foundation for building things. But I had not, every few years I understand. So, there came this moment when I realized, okay, documents can be represented as symbolic expressions. User interfaces can be represented as symbolic expressions. Lumps of computation in the cloud can be represented as symbolic expressions. Contracts can be represented as symbolic expressions. All these things and once you do that, you have this whole wealth of functionality that just operates on symbolic expressions that you can then immediately make use of. And that's kind of where a lot of the power that we end up having comes from, is everything is a symbolic expression, and everything that's been built for any symbolic expression can work on your particular symbolic expression. Now, as a process of language design, we have a whole effort called our little language completeness and consistency initiative, which is basically when we add a thing, where are all the tentacles that it have to connect to.
I know you have a big release coming up pretty soon, or it's just happened, or?
Oh, we have releases every, Wolfram Alpha, there's a new release every week. For Wolfram Language, it's about every 3 months that we have an incremental release. Our incremental releases have become absurdly large. We have version 12 coming up probably this summer, which is, it's interesting that we've got this whole, because we have this kind of well-structured language, sort of incremental delivery of functionality is rather easy. What we've tended to do is to have the point one releases be sort of everything the R&D pipeline has brought out, and then the integer releases, our kind of goal is to be able to tie in a bow areas of functionality, even though the component parts were already available.
Right,
and so for example, if we've been doing live. One of the things I've done last few months actually is we don't really have direct competitors. I suppose the Jupyter people took 28 years to understand our notebook technology. I was sort of amazed that people are that took 28 years for people to cotton on to our notebook technology, which many people have been using for a very long time. But anyway, we don't really have direct competitors. And so for me, it's kind of like we might as well, I think the intellectual process of designing our language is pretty interesting. So I thought a few months ago we'll just start live streaming this stuff. And so it's interesting. A bunch of people kind of tune in, make, there's some interesting suggestions that come out. They get triaged, because my goal is to actually do these meetings and get through our design process. But, when there are suggestions, somebody is triaging these things and sending me the interesting ones. And I think that's been, I don't think anybody's probably ever seen, that kind of language design process happening in real time. I don't know any other place where you'd ever see that. And it's perhaps a little, for me, I've been doing this for a long time. So the thing that of course happens, it's never perfectly smooth. It's hard, it's difficult stuff. It's the most difficult, language design is the most difficult intellectual thing I do.
A long time.
Human languages, as a designer of computer languages, human languages evolve. Computer languages are built and designed. And
they get tweaked and changed, but
maybe not ours. Ours is ours is, and it's an interesting responsibility because you're defining how people should think about things. I think it's also something where, I see it as being kind of the in the world of, we're building a lot of automation, which is kind of like, AI type stuff. And it's a question of how do we then express what humans actually want all this AI to do?
And so what are, over the next couple of small or large releases, what are the newer semantics and features that people can look forward to?
That is an interesting question. Let me think. What's coming in version 12? Well, okay, so here's an example of something. So we have a product called System Modeler, which is used by systems engineering people to design things like jet engines and so on, which are kind of complicated objects. So one thing we've been doing for the last 5 years, basically, that product was originally a company that used our technology stack to build the System Modeler product, and we bought that company, and we've been kind of integrating their technology into our core technology stack. And so one of the things that's come in sort of preliminary form but is coming in full form is for, I think there are like 10,000 kinds of objects, like, thermostats or, electric motors or whatever else, which are now representable in our language. So you can say, here's this object that is basically, the schematics for a washing machine or something, and here it's the representation in our language, and we can then treat that as a lump of computational work.
Yeah.
You can then say, what does this washing machine do if blah, blah, blah.
And it's great for automating through AI for simulating.
Well, it's for simulating devices, engineering devices. So it's just something you might not expect, but that's another thing where we have a symbolic representation now for, a washing machine, for example, for what it does. That's one area. I mean, another big area is our compiler technology, and a very fancy. Our language is a typeless language, in the sense that but we have a type analysis is useful for a bunch of purposes, and we will be exposing a very elaborate type system that's makes use of kind of modern symbolic ideas about types. So, I mean, most people who use our language won't see it, but if you want to analyze things in that way, I think we've been building out our machine learning stack a lot, and we've really achieved a high degree of automation in doing machine learning, and where that's being extended to, for example, audio, sequences of audio and things. A bunch of stuff with audio is coming.
Oh, really?
We've already got a bunch of stuff with audio, but we'll have
sort of like transcripting of it, or
yeah, we're going to have voice to text stuff. And speaker recognition and all those kinds of good things.
That's actually super interesting. I was in Israel last year, and I saw a very, very small company that had an interesting demo of something like this for meetings, like extracting to-dos and things from
right.
stuff, which was quite interesting.
Other things we have, there's a lot of deployability kinds of things which are in sort of continuous development, but one area, there's this thing we call Wolfram script, which is basically the command line access, and we have these client libraries for languages like Java and Python and so on. And one thing that I think is sort of interesting there is really being able to make use of Wolfram language just like a giant Python library or something. So
dependency and something else. That was actually something I was thinking of when you were describing aspects earlier, how to pull in the services into your...
Yeah, right. So you can use it you can instantly use it in the cloud.
Yeah.
Or you can have a local engine which you've installed and use the local engine in your software stack. And that's another thing that's coming. Let me see what else is coming. I mean, there are other things. We've been doing a big build out in computational chemistry, which is perhaps a more specialized thing. But it's kind of like, how do you represent a molecule symbolically?
And this is a big. I've met a lot, actually in Europe especially, and a lot of startups doing chemical modeling, pharmaceuticals, and things like that. It's actually a very big space. There's a lot of companies.
Well, it's a space that came and went, and now maybe it'll come back again.
I think it is coming back. Yeah.
Right. I mean, I think what we're able to do is very flexible and rather powerful, and it's basically here's a representation of a molecule, now compute features of this molecule. We're not doing giant proteins because that takes a giant computer to do it, and we're doing somewhat smaller molecules as things where we can compute all their properties. But I think it will be, I mean, again, it's always hard for me, you build something like this, and once you have it more or less built, you start to really understand what the power of it is. And let's see, what else are we building that's particularly relevant to developers? Well, I think a lot of stuff to do with deployability and integrating with. I mean, we've been doing. Well, some of these blockchain integrations are kind of interesting.
To keep an eye on those. Certainly, it would be. Yeah, the combination of the computational contract plus the artificial intelligence plus the kind of transaction to transaction is one of those very interesting aspects of blockchain, like machines talking to machines and exchanging currency between each other.
Well, I think that one of the things that's important in computational contracts is things which were human judgment calls that can be turned into machine learning calls. That is, is this really I don't know, how bad is my cold? If you can observe my various symptoms, make a distinction. Is it a, I don't know what the medical classification, what ICD-10 classification code should it be for my cold or whatever? Or is this piece of fruit really ripe? And I think anyway, so
it sounds like a lot of interesting things for many different people in many different spaces. I have one final question.
Yeah, sure.
Sort of after talking about all these fairly advanced things, this is actually a question from someone wanted me to ask, which takes it probably down a notch again. It's specifically said around Wolfram Alpha, but it could be in one of the other products as well. Although there's probably some potentially complex that maybe it's hard to answer. What's your favourite query?
A query. There's a party trick query, which is kind of fun in Wolfram Alpha, which is you type in somebody's name, and we'll do it just to see what See, I'm let's type in. Let's just try typing in Chris here. And let's see. Now, this is U.S. births because we're in the U.S., but this is saying that the most common age for a person, that's the distribution of people named Chris. Right. And the most common age is 49 years. Yeah. So the party trick that's often fun is you type in somebody's name, and just because of the way probabilities work and because these distributions can be quite heavily peaked, it's surprisingly common that the age you'll get out is actually their age.
I'm a little bit younger than that, but
fair enough. No, as a matter of fact, I just noticed a couple of weeks ago that my name, of course, I was born in England, so this data isn't really it's and the UK doesn't have such well-organized data, unfortunately. But I am, for once, I am actually the age that is the most common age, which is 58.
Amazing how old-fashioned our names are, isn't it?
Yes. Well, but you see, you can see, like with Stephen here, there were multiple peaks, which is presumably people...
really fallen off now.
Yeah. No, it's all gone now. There won't be any of those. And, and if you pick a name, I don't know, do you have children?
No, I don't. I have godchildren. His name is also Christopher. That's beautiful. Matilda, isn't it? I think they've all got old-fashioned names.
Right, let's see what that says for... Oh, wow. But it's had a resurgence. It was really big in the 1880s. Okay, the most common age for a Matilda is 2 years.
That's close. She is about 8 or 9. So yeah.
Oh, okay. Well, so the parents were ahead of the curve.
Yeah. There you go. Be a way of naming your child. So, like, what needs a revival?
Yes, right. What's you have to be careful. I have 4 children, and I one of my theories of child naming is, the name Kermit was a really good name until there was a frog by that. No, it's of course the thing that always is amusing about names sometimes is that people will have a certain name, and then you'll discover that they have a name, and they are like, somebody will be called Green, and it will turn out that they're a plant biologist.
Yeah.
And,
yeah. What was on the other day? I don't know. Yeah, this happens surprisingly often, actually. It's so coincidental that you are named after a computational language. It's a very strange coincidence.
Yes, right. Well, that's I'll tell you, this whole business about what should you, I struggled for a long time actually about what to call Wolfram language and whether to, and eventually, everybody inside our company had called it Wolfram language for ages, and it's just like, what the heck? And when I was naming our company,
sometimes it just is.
Well, although one of the interesting things with Wolfram Alpha, this is an interesting observation which I had never expected. Okay, so I go around, I give talks at schools and things like that, and so I run into a bunch of kids, right? And they use Wolfram Alpha pretty much. It's very almost universally used among high school students and college students and so on. And they'll meet me, they'll see my name, they'll say, "Are you related to this Wolfram Alpha thing that we use?" Say, "Yeah, that's my thing." And they're like, there's this moment where there's some kind of reset that happens when they realize, oh my gosh, this software that we use, somebody actually built that stuff.
Yeah, exactly.
People don't, I think the typical person doesn't realize that there's actual, some human has to figure out this is something that can be built and go and build it. But I think it's also the thing that's always nice about naming stuff with people's names and so on is it doesn't mean anything. I remember years ago I was I've seen too many companies where they gave a name that was like, I was a consultant for a while for a company called Thinking Machines Corporation, which actually I had a little input in the naming of that company, which I thought was a really cool name, except when it decided it wasn't an AI company and wanted to build supercomputers instead, it was a really bad name.
Okay, because it's thinking too long. Yeah.
And I think, what happened for us is the name Mathematica, which, I knew perfectly well at the beginning was too restrictive a name for the product that we had, but mathematics was its sort of first killer app, and actually I sort of blame Steve Jobs for encouraging me to actually use the name Mathematica for our product. And at the beginning it was a good name because people could immediately understand what the point was, and it was also, that was before the web, when there wasn't, when it wasn't as easy to understand what was going on. But over the course of time, it's just like, I am so fed up with people saying, I don't do math, so I don't need to use this thing. It's like, well, math is only some small fraction of what it does. And I think with Wolfram language, or the only thing that's happened with that right now is people hear the word language and they think, oh, it's like Python or something. And that's we thought about calling it sort of a hyper language or something, which is perhaps, but I think the correct intellectual description is language. And so that's what I
redefining language to bring it back to what language actually was.
Well, yes, and I mean, language, human language has lots of knowledge built into it, which is what if it was if all we talked about was if we were pure speakers of propositional logic or something, it'd be a different story. But that's not what language as we humans use it has ended up being.
And that was my interview with Stephen Wolfram at Collision Conference. If you have enjoyed the show, you can find previous episodes at gregariousmammal.com/podcast, support the show at /support, and find us on Facebook at facebook.com/gregariousmammal. And you can find me personally on Twitter at Chris Chinch.